So we're beginning chapter 5 by learning about factoring, and so I want to take it back even maybe a little before junior high, and we're going to look at prime numbers. And so if you see right here, I've given you what a prime number is. If you forgot, it's a number that can be divided by itself in 1. So it can't be divided by anything else, only itself in 1. And the way we're going to be looking at factoring today is we're going to be using prime factorization, which is basically we're expressing a number as a product of primes. And the way we're going to be doing that is we're going to be making factor trees. So usually everyone loves factor trees. Hopefully you guys do too. And so I'm going to review with you guys how to do factor trees, and then I'm going to show you how to write from a factor tree how to write something as a product of primes, and then also by using a factor tree how to find a GCF. Okay, so let's just review though what a factor tree is. And so let's say, and my little message is going to come up here, I think. There we go. Okay, so let's say for example I wanted to make a factor tree on maybe 504. Okay, 504. So that's a pretty big number. Some key things that if you're getting a little lost, get a calculator out, and remember, a factor tree first starts off as a stem of 2. Okay, and what you want to do is you want to think of two things that multiply together to get 504. So like I said, that's a pretty big number. So if you get to that point where it's such a big number, and look at this last digit, see how it's 4, and 4 is an even number. So if you get to that point, maybe see what happens when you take this number divided by 2, because an even number at the end will always, as a last digit, an even number as a last digit will always give you something divided by 2. Okay, so if you put that into a calculator, 504 divided by 2 is actually 252. Okay, and so if you found another number to work with, that's perfectly fine too. That's just if you're lost, try to if this is an even number, okay? And so the key thing is that these first two stems is that they should multiply together. The two things should multiply together to get to the tip here. So 2 times 252 should be 504. And then from there, we make another stem, so we need to find something divided by 252. So again, that's kind of a big number, so maybe since this last digit is even, let's do 2 again and see. So 2 times what here would be 252? It'd be 136. Okay, and if you notice, I ignored this 2 because we can do 2 and 1. If you wanted to do 2 and 1, we could, but you don't have to do that because it's a prime number already. And remember, a prime number is something that can only be divided by itself in 1, and so this is 2 would be a prime number, right? Because it can only be divided by itself in 1. It can't be divided by 4 or whatever. So we leave it there. So I'm just going to leave the prime numbers there. You don't need to expand them out. And same with this 2, we don't need to expand them out. So once you get to a prime number, just stop. Okay? But 136 can actually be split in again, so if you want, go by 2. If you want to use another number, that's fine. So 2 times what equals 136? 2 times 63. Okay? Again, now we have a 2 again, so I could leave it. What times what equals 63? 9 times 7. What times what equals 9? 3 and 3. Is there anything that can multiply to get to 7 other than 7? No. Okay, so I'm just going to leave that, and then basically all we have left now are all prime numbers. So just for the sake of being pretty here, what I like to do is I like to stem out all of my numbers, all of my prime numbers, so they all end up on the same line. Okay, so that's something you may not have done before. I would highly recommend it so you don't miss out on anything. Okay, so this whole line is all prime numbers. This line right here, this last line that I have right here. And so if you wanted to write a product of primes, basically 504 would be 2, and that we have 3 2's here, so it becomes 2 to the third, because there's 1, 2, 3 2's, times 3 squared, because there's 2 3's, 3 times 3, times 7. And that's how we would write that out as a prime factorization, as 504 as a prime factorization. So let's look at another one. Let's try maybe a little smaller number. Let's try 180. Okay, and so this one works out a little bit better, and I actually want to go back. Actually, let's go back to number 1. So right here when you split, it doesn't matter what factors you put. So if you found another pair that worked at the beginning, maybe not 2 divided by 252, but you found something else, it doesn't matter what you put down here, as long as they really do multiply to that number, you'll get this same bottom line. Okay, so I'm going to show you this with 180. So 180 can go into, we can do, what can we do? We could do 2 and 90, right? Or 2 and, what am I talking about? Yeah, 2 and 90. Okay, and so 2 is prime already. Maybe 90 can go 9 and 10. 9 can go 3 and 3. 10 can go 5 and 2. I'm going to drop that 2 down. Okay, so if I wanted to, so now I have a whole list of prime numbers. And so what I can do now is I can write it as a, write it as a product of primes, and so here we go. I have 2, and how many 2's do I have? I have 2 of them. I have 1, 2, so that becomes 2 squared, times 3. How many 3's do I have? I have 2, times 3 squared, and then 1, 5. And if you multiply all those guys together, 4 times 9 times 5, you should end up getting 180. Okay, now let's take 180 in a different way, and I'll show you that no matter what, you really do end up getting the same bottom line there. Okay, so let's say I did 180 as 6 and 30 maybe. Okay, so 6 splits into 2 and 3. 30 splits into, I don't know, let's do 6 and 5. I go 3 and 2 for 6, and I'm going to drop everything down so it's all on one line. Okay, and what do I have here? I have 2 squared, because I have 2 of them, times 3 squared, times 5. So I'm trying to show you that, see, these two lines match up. Even though we use 2 different numbers in the beginning, it still ends up being the same, so it doesn't matter. So don't worry if your stuff is not kind of balancing out, or if you think that you used different factors than me. You're going to get the same answer as long as everything really does multiply to what the top of your stem is. Okay, so I'm gonna let's leave you with one more that you guys can try by yourself, and I'll work this one out, and you guys can check and pause and see how it works out. So let's do 936, and you guys work on this and write it as a product of primes. So here we go. Alright, so what I want to do now is, now that you're kind of familiar again with with factor trees, I want to look at GCFs, okay? The greatest common factor. So I'm going to show you how to calculate the greatest common factor now. And that's also known as the GCF, okay? So let's say I asked you maybe to find the greatest common factor between 20 and 28, okay? So we're number 4, let's say I did 20 and 28, find the GCF. So what I want you to do is I want you to make 2 factor trees, one for 20 and one for 28. So here's 20, here's 28, and let's make a factor tree for each of those guys. So maybe 5 and 4, 5's prime already, 4 splits into 2 2's, so I end up with that. Okay, you don't need to put it into the product of primes right now, just factor it out, and leave that last line like that. 28 goes into 7 and 4, 2 and 2, and it looks like that. So looking at the last line of each tree, again, this is to find the GCF, okay? So looking at the last line of each tree, think of it like this. We are trying to make some matches here. This is, we're trying to find a date to the prom here, these numbers, okay? So trying to find a date, we'll make a date for homecoming maybe, okay? And when you find a date, you want to find someone who's almost exactly like you, or is exactly like you, okay? So looking between both of these trees here, do we have a match, a perfect match for 5 on this tree? No, okay? This tree does not have a 5, so it's not a good match. And same with going this way. There's no 7 on the other tree, so they don't match up. But here I have a 2. And do I have a 2 that's not spoken for yet here? I have a 2 right here, so I'm going to circle it because it's spoken for now. Those 2 are going to go to the dance together. I move on over and I have another 2 right here. And do I have a 2 on this side that's not spoken for? I do. So I circle it. And so to find the GCF between these two, you want to multiply these two circled numbers together. So 2 times 2 is 4. And multiply these two circled numbers. It's 4. So you want to make sure that both sides equal each other, okay? Which tells me that the GCF of both of these guys is 4. So if you make sure that both trees equal the same, then you're good to go and that number becomes the GCF. Okay. Let's try another one. Let's try, let's try 36 and 80. Okay, GCF for 36 and 80. So factor them each out. 80 could be 8 times 10, 2 times 4, 2, 2, 2, 2, and 5. Sorry, that's a super big 2. But alright, here's my last line here. Here's my last line here. So looking at this first tree, do I have a 3 on the other side to pair up with it? No. How about a 2? I have a 2 here, and I have a 2 here. We already established there's a 3 here, but there's no 3 on the other tree, so it doesn't count. I have a 2 right here, so I can circle one of these 2's. And so this tree ran out of numbers, so there's nothing left. So even though I have 2 2's right here, unfortunately I can't circle them because they have to be one from each tree. So these 2's cannot buddy up next to each other, okay? So that's it. So 2 times 2, multiply the circled number is 4 on this tree. Circled number is 4. They both are okay on both trees, so my GCF is this number. Okay? I am going to step it up for you really quickly here, and I'm going to find the GCF for 3 numbers this time. So let's go 100, let's try 120, and let's try 90. Okay? So same idea, we're going to make a factor tree for each of these 3. But this time, instead of finding just a matching one in 2 trees, they have to have 3 of a kind this time. Okay, so it's not as simple, unfortunately, as we had it before. So I'm going to show you what I mean here as I factor these guys quickly for you. So if we went 9 and 10. Okay, so here's my last line here. Here's my last line here, and here's my last line here. So starting right here, I have a 5. Do I have a 5 in the next tree? Yes. But do I have a 5 in the next tree? Yes. All 3 of them have a 5, so I can circle them. They're spoken for now. They're going to the dance together as a trio. Okay? Looking at the first tree, I have a 2. I have a 2 here. But do I also have a 2 there? Yes, I do. So those ones are good to go. First tree again, I have a 5 here. I have no more 5 in the second tree or in the third tree, so I can't circle that. I have a 2 here in the first tree. Ooh, I have a 2 here in the second tree too. Moving on to the third tree. But I have no more 2's in this third tree, so unfortunately they can't go as 2's, they have to go as 3's. Each tree has to have the number. So even though this 100 has the 2 and this 120 has the 2, since this 90 doesn't have a 2 that's not spoken for, we can't circle them. So multiply all the circled numbers together. We got 10, 10, 10, so we know that we are good to go. So our GCF between the 3 of these guys is 10. Okay, so something to remember if we're doing multiple ones is that if we're doing multiple things to find the GCF between is that they have to, all 3 of them have to have the, every single tree has to have the number not spoken for. So that's why even though in this last 2, even though there was a 2 there to buddy up with, since we were looking for 3, we're looking for a GCF between 3 numbers, there has to be 3 2's. So I have, when I jump over to this tree, there's no more 2's, so I cannot, they can't buddy up anymore, okay? So, just something to think of. Please write down any questions you have. I hope this was a review, or if it wasn't, that's okay. I don't mind going over it again tomorrow in class, so please ask me some questions if you have any about this GCF and stuff, okay? So don't forget to take the quiz, and we are good to go.